let's dive into a truly mind-bending idea that's shaking up the world of physics. What if our entire universe, down to its very core, is basically a giant quantum computer? And the key to unlocking this whole thing? Well, it might be hidden inside the most mysterious objects we know: black holes. Everything really kicks off with this one question. We know they're out there. We've even managed to snap a picture of one's shadow. But what's actually going on inside? What happens once you cross that point of no return? It is, without a doubt, one of the biggest puzzles in all of science.
And the reason this is so tough is because our two best theories about the universe just don't get along. We've got general relativity, which is brilliant for describing gravity, planets, galaxies, all the big stuff. And then we have quantum mechanics, which is absolutely perfect for the tiny subatomic world. Both work flawlessly in their own domains, but they completely clash.
And a black hole, well, that's the one place in the entire universe where you need both theories to work at the same time. You have this insane amount of mass crushed down to a single, infinitely small point. And right there, at that singularity, our understanding of physics just stops. It breaks. And that's exactly why black holes are the perfect laboratory for finding a new, unified theory of everything. So, where do we even start looking for clues? Well, our first lead comes from the quantum world, and it's a concept you've probably heard of: entanglement. This is that really bizarre, spooky action at a distance, as Einstein called it. It's where two particles get linked in such a way that if you measure one, you instantly know the state of the other, even if it's clear across the galaxy. It's weird, for sure, but it is very, very real.
So, over the past decade or so, a really radical idea started to bubble up. One that tried to connect this spooky action to the very fabric of the cosmos itself. Honestly, it was a leap that sounded like it came straight out of science fiction.
The idea was this: what if entanglement isn't just something happening in space, but is actually what creates space itself? There's this proposal, you might hear it called ER equals EPR, that suggests a wormhole, a bridge through spacetime, is really just the other side of the coin for quantum entanglement. So in this picture, two entangled black holes aren't just magically linked. They're literally connected by a physical tunnel through spacetime. And this isn't just some fringe idea. Listen to how physicist Javier Martín Garcia puts it. The way quantum states are entangled plays a significant role in the geometrical structure of spacetime. This really gets to the core of the holographic principle, the idea that quantum information living on a flat 2D surface could be creating the 3D gravitational reality we experience inside of it. So this was huge. It looked like we were finally connecting the quantum world with gravity in this beautiful, elegant way. But you know how it goes. As physicists started to dig in, they hit a major snag, a paradox that really threatened to bring the whole beautiful idea crashing down. Okay, here's the first part of the problem. When a black hole forms, its entanglement entropy, which is just a fancy way of measuring its internal quantum disorder, grows like crazy fast. But then, pretty quickly, it just stops. It hits a maximum value and just stays there, totally settled. Physicists call this thermal equilibrium. But here's the kicker. According to general relativity, that wormhole on the inside connecting the two black holes, it never, ever stops growing. Its volume just keeps increasing, forever. So hold on. The quantum side looks totally static and settled, but the geometry side is changing and growing forever. They don't match. Entanglement can't be the whole story. And this is the absolute crucial question. If the entropy maxes out but the geometry inside keeps on growing, we need to find something else. We need some other quantum property that also keeps growing for an incredibly long time, long after the system looks like it's settled down. And that new suspect, the new hero of our story, is a concept called quantum complexity. It's an idea that actually comes from computer science, but it might just be the missing piece of the gravity puzzle. So how in the world do we think about complexity? Well, the best way is to imagine a Rubik's Cube. A solved cube is a really simple state, right? Its complexity is basically zero. But a scrambled cube, that's a complex state. And the complexity is simply the smallest number of moves you'd need to make to get from that easy solved state to that specific scrambled mess. It's a measure of how hard it is to create that state. And this is the aha moment. This is how it solves our paradox. Just look at this. For a quantum system like a black hole, the entropy, the disorder, it maxes out super fast and then just flatlines. But its complexity, the number of computational moves needed to create that quantum state, it just keeps growing and growing for an almost unbelievably long time. That endless growth is exactly what we needed to match the endless growth of the wormhole. And this all leads us to this massive new idea, holographic complexity. The conjecture is that what we see as the growing volume inside a black hole is actually the geometric twin of the growing quantum complexity on its surface. Space-time geometry, it's not just about entanglement, it's about computation. Okay, so right now, physicists are exploring two main flavors of this idea. One is called complexity equals volume, and it's pretty straightforward. Complexity is just proportional to the volume of that growing wormhole. The other is called complexity equals action, which is a bit more abstract, linking complexity to things like energy and momentum in a specific chunk of spacetime. But the key thing is, even though they're different, they're both trying to get at the same fundamental connection. And here's the really amazing part. Even though these two ideas calculate complexity in different ways, they both spit out the exact same answer for how fast it grows over long periods. They both predict that the growth rate is directly proportional to twice the black hole's mass. In physics, when two different paths lead to the same answer, it's a very, very good sign you're onto something real. But look, this idea is so much bigger than just tidying up a paradox about what's inside a black hole. If complexity really is the secret code to understanding geometry, it gives us a brand new, incredibly powerful tool to probe the deepest secrets of our universe. I mean, think about what we could do with this new lens. We could potentially study the singularity at the heart of a black hole, a place our current theories can't touch. We could get a much deeper grasp on the thermodynamics of black holes, and maybe most profound of all, it might give us a totally new way to think about why time only ever moves forward. Essentially, complexity could be a more natural language for describing these extreme places in the universe. Think of it like this. Entropy is like a thermometer. It tells you when the system gets hot and reaches equilibrium, but then it just stays put. Complexity, on the other hand, is like a detailed clock that just keeps on ticking, giving us more and more information long after the thermometer has maxed out. Which leaves us with this final, absolutely profound question. For a long time, we thought the arrow of time came from entropy, that things always get more disordered. But what if that's only part of the story? What if the real reason we can't turn back time is that the universe is constantly performing a calculation, and its complexity is always increasing? What if the forward march of time is just the universe computing its own future?